Hi, and welcome to Statistics 1, Lab 2. The goal of this week's lab, or goals of this week's lab, are 1, to read a data file into R. Then we're going to learn a little bit more about object types. Then, since the topic of this week's lectures was mainly distributions, histograms, and summary statistics, what we'll do is we'll print some summary statistics in R, and we'll examine distributions using histograms and the hist function. So you can see that I'm in the R editor already. So this script will be available on the course website, so you can follow along. And this will be how I'll start each lab. So we have a script, and as I did with Lab 1, I'll just walk you through this script. I'll execute just lines of code at a time. And then we'll go to the R console, we'll see what output we get. And this week we're going to look at some graphics. So we'll move to exploring the graphics output as well. Just a couple of notes before we start. You've noticed, particularly in the discussion forums, that there's almost always, more than one way to do something in R. So be patient. And if you come up with a more efficient way to do something than I've demonstrated here in my script in lab, then feel free to share that with the rest of the students. You've already done that in the discussion forums, and that's wonderful. But again, just be patient and be polite as you're sharing that information. It's a wonderful opportunity that we have here in these discussion forums. Okay, so let's launch into Lab 2. As I said, here are the lab goals. And each week what I'll do is I'll pick a particular example. And this week I'm going to go back to the example of a study that investigates the effects of sports-related concussion on memory and attention. And one of the reasons I'm picking this as an example is, well, 1, we talked about it in lecture, but 2, you can actually go look at this test. It's available online at the following website, impacttest.com. So you can learn more about it if you like. And Impact, or impacttest.com, provides 6 main measures. And those 6 main measures are verbal memory, visual motor speed, a general reaction time measure, a measure of impulse control, and then just a total symptom score. Just how many symptoms are you experiencing related to a concussion. The way this research works typically is athletic directors or coaches in sports, they administer this impact test to their athletes both before and after concussion. So they get a baseline measure, and that's what we're calling some of our variables in today's lab. And then after a concussion, they measure them again. So having that baseline is very helpful because you can see if an athlete has changed from baseline to post-injury. Without the baseline measures, it would be harder to detect. Okay, so let's get started. Another thing I didn't mention in the first lab is this notion of a working directory. And I must admit, I purposely avoided it because setting the working directory is different depending on what kind of computer you're using, what kind of operating system. But one universal is that there's a function in R called getWD, and that'll tell you what your working directory it is. So let me execute that, just one line of code. And again, I wasn't clear in Lab 1 how I'm doing this. And again, it's because it's slightly different on different computers and different operating systems. But I'm working on an Apple machine with the OS X operating system. So what I'm doing is I'm hitting Command Return or Command Enter. And I believe in most Windows machines, it's just Control Enter. So I'm just going to execute that. And then to go to the R console, I just do Command 1 on an Apple machine. If you're on a Windows machine, it's just Control 1. So I just flipped over to the console by hitting Command 1, and I executed getWD, and here is my working directory. And I can go back by doing Command 2. Again, if you're on Windows or perhaps another system, perhaps it's Control 2, and I'm back in my script in the R editor. So I commented out these lines because I don't need to reset my working directory. And again, if it isn't clear by now, anything that follows this pound sign, or if you're on Twitter, a hashtag sign, anything that follows that is a comment in R. Sorry if I didn't make that explicit in Lab 1, but it should be clear by now. Up here, like these are all just comments because they follow this pound sign. Okay. Another thing you will need to do, most of you will most likely need to do, is install one more package. You should have already installed the psych package. If not, no problem, do it now. Again, I've commented it out because I've already installed the psych package, and this new package, SM, is a package that we'll use just for this lab, and you'll see really just for the last couple lines of code. But go ahead and install those. I'm not going to do it in lab, and going forward, this is going to be how I'll do this in lab. I'll install them ahead of time so that I'm not wasting time here in this lab waiting for things to download. So I already did that, but you can maybe pause and go ahead and install those packages if you don't have them. Okay, so the next step, usually the first step at the beginning of a script, is to load the packages that you'll need to execute this script. So I'm going to go ahead and load psych and SM using the library function. And R doesn't really return anything for that. It may just tell you what version these packages are consistent with, but now I know they're loaded. And again, I asked, how can you check to see how which packages you have loaded? The way I demonstrated that was just by doing search. That shows you what packages you have loaded. So you can see here I indeed have the psych package loaded. I do indeed have the SM package loaded. And I did it that way because it just returns just a little bit of stuff. It gives me some other things, just things that are in my working directory. As a couple of students pointed out in the discussion forums, you could also use the function installed.packages, and that gives you a list of all the installed packages. I purposely didn't use that function because look, I have so many loaded here, and I'm actually not on my own desktop computer. I record these in a recording studio for sound purposes. If I did this in my office, it would be too loud. But there they are. So we do know that it's there. So again, there's typically more than one way to do things in R, and that's fine. That's actually one of the great things about it. Oops, I don't want to exit. Let me just go back to the script. Okay, so now we have the necessary packages loaded. Now what we want to do is read in the data for this week's lab into a data frame, and I'm going to call this data frame impact. The data live in is a phrase maybe common only in the US. The data exist in a file called stats1 data files stats113 lab2.txt. I know it's sort of a long name, but this is our internal name for our data files. We're calling things stats1 for statistics 1, 13 for 2013 because I did this course last year. Perhaps we'll do it again next year. And this is lab 2. And we tend to just save the data files as text files and then read them in using the read table function. But there are other ways to do this. You could save data files as .csv, for example, and there's a read.csv function. There are many ways to do this. But for this course, I'm just typically going to save things as .txt, post them on the course website as .txt, and use the read table function. There's also this argument header equals true. I could write out true, but you don't have to. You can just write header equals t. What that means is the top row of this file stats1 data files, stats113 lab2.txt. The top row of that data file, it consists of variable names. It doesn't actually consist of the data, or it doesn't contain data per se. It's just the variable names. So by setting header equals to true, I'm telling R that the first row contains the variable names, and then every subsequent row will contain the data. And so if I execute this line of code, again, I'm going to do command 1 to go back to the R console. It seems to have worked. It doesn't return anything, but it didn't give me an error. So that's good. So how do we know if it's there? And this is one of the things that's difficult as you transition from something like Excel or SPSS or Stata. And I know the frustration that is out there because I did this myself just a couple years ago. I transitioned from SPSS, and I used SPSS for almost 20 years. So it was difficult. So one of the difficult things is you can't see your data, right? Like where is the data? So one thing you can do is just say, well, I want to know the dimensions of this data frame. That's always helpful to me, someone who's used to thinking about data frames, data structures, and matrices. So I can just ask R, well, what are the dimensions? How many rows? How many columns? So I'm going to use the functions dim, nrow, and ncol. Execute that. Go to the console. Dim impact gives me 40 and 14. What that means is there's 40 rows and 14 columns. And typically there's in psychological research or medical research, which I would call this more medical research, a row represents an individual person. So there's 40 athletes represented in this data set, and there are 14 columns worth of data. So if I ask just nrow, of course, I'll get 40, ncol 14. Okay, let's go back to the script. But what if you really want to see your data? I understand that. I like to see my data. So one way to do that is to just use the edit function. So if I execute edit impact, then it brings up the R data editor. And now you can see your data. But be careful, it's an editor. So you could edit your data in here, meaning you could accidentally make a mistake in here and change one of your values. Okay, so you have to be careful when you do open up R data editor. And let me also say, if you're working with RStudio, then you might already see your data. So I'm not working with RStudio. If you are working with RStudio, that's fine. So what you see here is the first column is just a subject ID. So this is typical in any kind of research. We give these sort of anonymous ID numbers. We don't use people's names, right? Because we want it to be confidential. Then what condition are they in? So we have some athletes who are just in a control group, and then we have some athletes who are concussed. And then we have all these measures from the impact assessment tool: verbal memory, visual memory, motor speed, reaction time, impulse control, and symptom score. And we have them at baseline. So these are all baseline. And then we have them at retest. And I call it retest, not post-injury or post-test, because remember, this control group, they're not concussed. So they're getting all of these things at baseline, and then just months later to match the concussed group in time. So we're just calling that retest. Okay, so let me close the editor. And now we're back in the script. Let's talk a little bit more about object types. We covered this a little bit in Lab 1, but just let's reinforce this. So if I just do class impact and names impact, then it's just going to tell me, well, impact is a data frame. Hopefully you should know that by now. So I read the data into impact. R interpreted that as a data frame because it's a matrix consisting of all sorts of variables of different types. If I type in names, it just gives me the names of all the variables in the data frame impact. So back to the script. This is an important piece of code right here because you often want to access one variable in your data frame. And the way to do that is by naming the data frame, then $, and the variable name. So if I ask what class is verbal memory baseline or reaction time baseline and so on, what will R return? So for class impact verbal memory baseline, well, it says, well, that's an integer. Reaction time, that's numeric. You'll see if you go back to, it's actually on the screen up here, that's convenient, or you could go back to the editor. You'll see verbal memory baseline, I believe that's this column here, these are integers. Reaction time is typically measured more precisely, typically on the level of milliseconds. So you'll see we have things like 37.46. So R interprets that differently and calls that numeric. Notice here that subject is interpreted as an integer. And we don't really want that to be interpreted as an integer because we just used numbers, but it's really a nominal variable. If you think back to the lecture on variable types, it's nominal. We ideally would put the subject's name in there, but for confidentiality reasons, we often just assign a number. So we might want to change that. So let's go back into the script. And there's a very easy way to change that. I can use this function factor to change the class of that variable. So let me execute that line, or 2 lines. And now what you see, if I ask R, what is the class of the variable subject in the data frame impact? Now it's a factor because I use this factor function. And that's better because subject it's not numeric. It's, subject 40 is not greater than subject 39. Those are just arbitrary numbers that we assign to our subjects. So let's go back to the script. Okay, so now let's switch gears a bit and go to summary statistics. And this was one of the main topics of lecture this week, is getting summary statistics. So there are functions in R like mean and standard deviation, so mean and SD. And I could do that for one variable like verbal memory baseline. So I'm going to execute that, go to the R console, and it gives me the mean of verbal memory baseline. It was 89.75. And this was out of 100. So these athletes at baseline are doing very well on this task, but that's to be expected. It's not that difficult of a task if you look at the website impact. And they're not concussed. They're healthy college athletes, so they're doing well. The standard deviation is about 6.4. In the next assignment, we're going to ask you some questions where you have to, the answer will be a numeric value like this. And what we'd like you to do is respond just with 2 significant digits. What do I mean by significant digits? Well, in this case, the answer we're looking for is 6.44. You can stop right here, is my point. You don't have to type in 6.444039. That gets a little tedious. We'll code it so that if you do, you'll get it correct. But all we're asking for is 2 significant digits. So if this were 6.447, then you should round up to 6.45. That's what we mean by 2 significant digits. Okay, let's go back to the script. So that's a way of getting the mean and the standard deviation. You could get the median, the variance, and so on. But R has this really nice, handy describe function that does all of that for us for all the variables in the data frame impact. So there we go. This is a really nice function that we'll use a lot. It just gives us an overall summary of what's going on in our data. So it shows us all of our variables going down these rows. So verbal memory at baseline, visual memory at baseline, and so on. And then at retest, there are 40 athletes in this data frame. It gives me mean. It gives me standard deviation. It gives me median. R gives a trimmed mean, which trims some of the outliers or extreme scores. It gives you this other measure of variability called MAD, which stands for Mean Absolute Deviation Score. So remember when we calculated standard deviation, we first got the mean, then we got deviation scores, and then to get rid of sign, we squared all the deviation scores, and then we summed them to get sum to squares. A different approach, which is sort of unusual, and R is one of the only software packages I know that includes MAD as a default summary statistic. But what you could do is instead of squaring to get rid of sign, you could just take the absolute value of the deviation scores and then average those. That's what MAD is. We're not actually going to use it very much, but I just wanted to point that out to you. R also just tells you what the minimum value on this measure is and the maximum value, and the range, that's just the difference between min and max. And then it gives us the skew and the kurtosis, the actual values. SE stands for standard error, which I'm just going to leave out there for now. We're going to talk a lot about standard error in 2 more weeks in lecture. But it's very easy to calculate. It's just the standard deviation over the square root of n. Okay, but back to the script. You might also want to look at those summary statistics by some categorical condition or by an independent variable, or in this case, a quasi-independent variable, right? Because this is the sports-related concussion example. So if we want to do that, we can use a function called describe by. So I use the describe by function. I want to look at the impact data frame, and I want to split it by condition. Condition was the name of the column that tells me whether an athlete is in the control group or in the concussed group. So if I execute that and go to the R console, now I have my summary statistics first for the concussed group and then for the control group. And it orders them that way just because it does it alphabetically. So concussed comes before control alphabetically. And then all the same summary statistics. So now let's go back to the code or to the script. You can also subset your data frame. And I know if you're coming from something like Excel or SPSS or Stata, you probably know how to do that very well. And it's typically like in a drop-down menu, like in SPSS, you can just do data split file. It's just as easy in R once you know the functions. So again, let me just run this edit function one more time to make clear what I'm about to do. So let's bring back up the data frame so we're looking at it. What I want to do is I want to just look at the athletes that are in the control group, so just these athletes, and I want to do some statistical analyses just on them. So I just want to subset that group. And likewise, then I want to subset just this concussed group. So how do we do that in R? Again, there are many ways to do this in R, so I'm just going to show you one. This is the way my lab tends to do it. So I'm going to create a new data frame called control for the control subjects. And I'm going to use a function called subset. I'm going to subset the original data frame impact, and I only want athletes who are in the control condition. Well, how do I tell R to pick out just those athletes? Well, I'm going to use this this system, which looks a little may look a little intimidating at first, but remember, the way to access a cell in a matrix is by typing the name of the matrix, or the data frame in this case, impact, then open bracket, and then row, comma, column. So it doesn't really matter what row they're in, but if they're, or I want to know what column contains the string control. So whenever column 2, which is the condition column, whenever column 2 says control, I want to take those athletes and put them in this subsetted data frame called control. Sorry, that was a little clunky, so let me just show you how it works. So what I did is I ran that subset, and then I just said, let me see the control athletes, and what it does is it just gives me 1 through 20. Let me go back to the script and just do it again for concussed. Again, I know that might have been a little confusing, so I'm just going to do it again for the concussed. We're going to say, I'm going to use this function subset the original data frame impact, go into that data frame impact. I'm not worried about row right now. I just want to look at column 2 because that's condition. If column 2 equals concussed, then I want to take them out and put them in this concussed data frame. A couple other things about this line of code that's illustrative of how R works is from now on, you'll see in lab 1, I didn't use this assignment function. Basically because I just wanted to get some of the basic points across. But whenever we assign like a new data frame or a new vector or things, we should be using this arrow and dash. This is saying assign this subset of the impact data frame to this new data frame called concussed. So that's a way to do assignment. You could put equals here, but if you do that, then it starts to get confusing when you're reading big scripts with lots of code because, like, look down here in this hist function, we're using the equal sign to assign values to arguments. So let's just use equals to do that, not to assign, for example, new data frames. Another thing is here, we're not saying, does this equal concussed? We're using equal equal. So we use a double equal if we're looking for R to return a true false or Boolean expression. So that's, I know, a little confusing when you start out, but there's just basically 3 ways of assigning. One is this guy right here. We're going to do that when we're taking something and assigning it to a new object or new data frame. There's equals. We're typically going to use that, like down here, which I'll show you in a second, as assigning options to arguments in a function. And then equals when we want R to return a true, false, or Boolean expression. Okay, so did I run this line of code? I can't remember. Let's just run it. There we go. So now we have 2 new data frames, one called control, one called concussed. So let's go back to the script. Now the last thing I want to do in this script is just show you how to do histograms. So it's real easy. There's just a function called hist. And again, this may look sort of confusing, but what we're doing is I want to do histograms of all the control athletes at baseline. Remember, there were 6 measures, so I'm going to do all 6 measures on one page. I want to do verbal memory, visual memory, motor speed, reaction time, impulse control, and symptom score. I want to look at all the histograms on one page so I can just get a glimpse. So the way to do that is to execute this one line of code right here. And what this says is set a parameter. That's what par stands for. And MF row is matrix formation by row equals combine 2, 3 or concatenate 2, 3. So basically what this is going to do is it's going to set up 2 rows and 3 columns to give me 6 histograms per page. This is like in Microsoft Word or Adobe Acrobat when you want to print multiple sheets per page. That's all this line of code is allowing us to do. So I'm just going to do all of this in one fell swoop. And boom. We've got 6 histograms on one page. So the first one here is verbal memory. The second one is visual memory, then motor speed. Then down here is reaction time. Down here is impulse control. And then here's symptom score. Remember, these are control athletes at baseline. So look, most of the athletes have a score of 0 or less than 0. There's one athlete out here who maybe exhibited one symptom. Maybe they just weren't feeling well that day. So these are healthy athletes because they're in the control condition, and this is baseline. One other thing I want to point out is this first histogram, verbal memory, it doesn't have anything at the top, notice. The second one, and all the rest for that matter, have at the top histogram of control, bracket, :4, because that's how we were calling visual memory in this data frame. I prefer this. It's cleaner. I have verbal memory right down here. I don't need anything at the top really. So that's why I put in this one histogram, in this line, I wrote main equals just open quote, close quote. So I puts nothing there. That way there's nothing at the top. It just makes it cleaner. So again, to reinforce this point that there's almost always more than one way to do stuff in R, I'm going to just show you that we could use this sort of fancy code of control open bracket blank comma 3 just to get the third column in this data frame. That might be confusing if you're starting out in R. So a more intuitive way probably would be to just name it by its variable name, right? So I could just say do a histogram for the control subjects of this variable, verbal memory baseline, and put the X label, label the X-axis verbal memory. These are equivalent. So just to demonstrate that, I'm going to run this. And if you look at these two histograms, they're exactly the same thing. So that's just demonstrating there's two ways to call this variable. And what I mean by call is to access that variable in R. Okay, so these two histograms are exactly the same. In my lab, we like to use this system, right? Because it requires less lines of code, and it's just more efficient. And I like doing it at the beginning of this course because it's sort of forcing you to start thinking in terms of matrices and data frames, which is really important going forward in the class. Okay, so the next thing we can do is look at histograms of the concussed group at baseline. So let me just run all of that. And there we are. Again, this is the concussed group, but at baseline. So let's zero in here on symptom score. Again, it's just everybody's down here at 0 because it's baseline. We're almost done with this lab. Hang with me. If I now look at the control group at retest, none of the histograms change very much. Again, I want to attract your attention here. Again, symptom score is very low. Of course, what's going to happen, you'll see now, if we look at the concussed group at retest. So this is after an injury. Now what you see, again, let's just go right over here to symptoms. Now you see symptoms all over the place. So these are the injured athletes after a concussion. And if you want, you can inspect these other histograms or look at summary statistics. You can see that their performance drops on a lot of these measures. Indeed, there are effects of concussion. Of course, we simulated these data to make it up, but this reflects actual research that we're doing here at Princeton. One final thing I want to show you. I know this lab is running long, but one more thing because it's sort of cool. And this is what we needed that SM package for. So instead of just doing a histogram, we could do what's called a density plot. And that's basically just a smoothed histogram. Let me show you what I mean by that. And I'm just going to use the symptom score from the injured athletes to show you what this looks like. So here's that histogram I just mentioned. These are the injured athletes at retest. So now you see symptom scores all over the place. And on the right, this guy is a density plot. What that's doing is it's smoothing this histogram. It's sort of best fit to this distribution. So it's nice, particularly for this kind of I was going to say experimental design, but I should say quasi-experimental design, right? You could compare density plots using a function called SM density compare, and that function only exists in the SM package. That's why we needed to install that. So this is the last thing I'm going to do in this lab. Let me run that one. And this really, I think, illustrates the effect of concussion, right? So in the green dotted line here, these are the control subjects at retest. So they're still hovering right around 0 symptoms. They're not exhibiting any symptoms. But look at the red line. These are the concussed athletes at retests. They're exhibiting lots of symptoms, and there's a lot of variability in the number of symptoms that they're exhibiting. And this is true of the research that I've seen on concussions. So, athletes out here are exhibiting lots and lots of symptoms. So these athletes must have suffered a really serious injury, whereas maybe these athletes down here, maybe they experienced, certainly they experienced an injury, but maybe less serious than out here. So there's some variability in the symptoms within that group. So that's sort of a cool graph you can do using this SM density compare function, and that lives in the SM package. And that's it for Lab 2. That's everything you'll need to do and to know to complete Assignment 2. So good luck with that, and I look forward to hearing from you in the discussion forums.